Proxima Centauri, the closest star to our planetary system, has long been a subject of interest for space specialists. This little red dwarf, discovered in 1915 by Scottish astronomer Robert Innes, is part of the Alpha Centauri system, which also includes Alpha Centauri A and B. Despite its proximity, just 4.24 light-years away, Proxima Centauri remains invisible to the naked eye due to its low brightness. However, it holds great scientific significance, particularly as the host star of Proxima B, an exoplanet that orbits within the star's habitable zone. Red dwarfs like Proxima Centauri and others such as Tauri are smaller, cooler, and much longer-lived than stars like our Sun. Their low luminosity makes them difficult to observe, but it also means their habitable zones are much closer to the star. For Proxima Centauri, this means an orbital distance of approximately 0.05 astronomical units, just a small fraction of the distance between Earth and the Sun. However, this proximity exposes Proxima B to severe stellar activity, including frequent solar flares and high levels of radiation, making its climate vastly different from Earth's. The discovery of Proxima B was a significant achievement in exoplanet research. Using the radial velocity technique, astronomers detected subtle wobbles in Proxima Centauri's position, caused by the gravitational pull of an orbiting planet. These wobbles allowed scientists to estimate the planet's mass and orbital period. In 2016, the European Southern Observatory officially confirmed the presence of Proxima B, marking a milestone in the search for potentially habitable worlds beyond our solar system. While ground-based observations have provided valuable insights, they come with significant limitations, such as atmospheric distortion and light interference, which hinder the ability of Earth-based telescopes to capture detailed data about the planet's surface or atmosphere. Most of what we know, such as its mass, distance from the star, and orbital characteristics, comes from indirect measurements. To uncover further details about Proxima B's environment and its potential for life, advanced observational tools like the James Webb Space Telescope, JWST, are essential. Proxima Centauri's role as the closest star system to Earth offers a unique opportunity to study exoplanetary systems. Proxima B, in particular, presents an exciting possibility: a rocky, Earth-sized planet within the habitable zone, with the potential to host liquid water and perhaps even life. However, the challenges posed by its harsh environment make it a complex puzzle for researchers. JWST is a revolutionary tool in the exploration of space. As the successor to the Hubble Space Telescope, JWST was built to overcome the limitations of its predecessor, particularly in observing the universe in infrared frequencies. This capability allows it to peer through cosmic dust and uncover features hidden from Hubble. One of JWST's key design features is its large primary mirror, spanning 6.5 meters in diameter, more than twice the size of Hubble's mirror. This larger mirror enables JWST to collect more light, making it capable of observing even the faintest and most distant objects. The mirror is coated with a thin layer of gold to enhance its infrared reflectivity and is made up of 18 hexagonal segments. Another remarkable feature is its 5-layer sun shield, which keeps the telescope's instruments at a stable temperature of about -233 degrees Celsius. This ultra-cold environment is necessary to detect faint infrared signals without interference from the telescope's own heat. Unlike Hubble, which orbits Earth, JWST operates from the second Lagrange point, L2, about 1.5 million kilometers from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to maintain continuous observations. JWST can study everything from the earliest galaxies to the atmospheres of exoplanets like Proxima B. Its ability to detect infrared light is particularly important for studying redshifted objects, those whose light has been stretched to longer wavelengths as the universe expands. JWST is designed not just for observation, but to answer fundamental questions about the origins of galaxies, the formation of stars, and the conditions necessary for life on other planets. With its advanced instruments, including the near-infrared camera NIRCam, the mid-infrared instrument MIRI, and the near-infrared spectrograph NIRSpec, JWST is a revolutionary research tool, a time machine, and a symbol of human ingenuity. Proxima B has captured the imagination of both scientists and the public as a potential second Earth. Situated within the habitable zone of its star, it has the right conditions to support liquid water, an essential component for life. With a mass roughly 1.17 times that of Earth, Proxima B is likely a rocky planet, comparable in structure to our own. Its proximity to Earth, just over 4 light-years away, makes it an ideal target for studying the potential for life beyond our solar system. However, Proxima B is far from an ideal twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual sunlight while the other is in eternal darkness. This creates extreme temperature contrasts between the two hemispheres, with the region where day meets night, known as the Terminator line, potentially offering a limited habitable zone with conditions mild enough to support life. The challenges of Proxima B's environment are considerable. Its host star, Proxima Centauri, is a red dwarf known for its intense solar flares, which release bursts of X-rays and ultraviolet radiation. These flares could strip away the planet's atmosphere over time, exposing its surface to the harshness of space. If Proxima B retains any atmosphere, it likely requires a strong magnetic field to protect it from radiation. Without such protection, the surface environment would be hostile to life as we know it. Despite these challenges, scientists remain hopeful about the potential for life on Proxima B. The planet's location within the habitable zone suggests that liquid water could exist either on its surface or in subsurface reserves. Life could potentially adapt to the harsh conditions, just as Earth organisms thrive in extreme environments like deep-sea hydrothermal vents or high radiation zones. The search for life on Proxima B is more than just a scientific endeavor. It is a quest to answer one of humanity's oldest questions. Are we alone in the universe? Proxima B represents an intriguing possibility, a rocky, Earth-like world that could harbor the conditions necessary for life. As technology advances, so too does our ability to explore this fascinating planet and uncover its secrets. However, the environment of Proxima B is heavily influenced by the nature of its host star. Unlike our Sun, Proxima Centauri is a red dwarf, smaller, cooler, and significantly less luminous. Its reduced size and temperature mean that its habitable zone is much closer, pulling Proxima B into an orbit just 0.05 astronomical units from the star. About 20 times closer than Earth is to the Sun. This proximity creates a unique set of challenges for the planet and any potential life it might harbor. One significant issue is Proxima Centauri's stellar activity, particularly its frequent and intense solar flares. These flares release high doses of X-rays and ultraviolet radiation, which are far more common and powerful in red dwarfs than in stars like our Sun. For Proxima B, this means a constant influx of high-energy particles that could strip away its atmosphere over time. Without a protective magnetic field, any atmosphere on Proxima B would be vulnerable to erosion, leaving its surface exposed to harsh radiation. Even if Proxima B retains some of its atmosphere, the radiation from Proxima Centauri presents significant challenges for life. High levels of ultraviolet radiation can break chemical bonds, preventing the formation of complex organic molecules. This could severely limit the potential for life to develop or sustain itself on the planet's surface. On Earth, organisms like Deinococcus radiodurans have developed mechanisms to repair DNA damage caused by radiation, suggesting that life on Proxima B might also adapt. However, the level of radiation resistance required would be extreme, possibly necessitating entirely new biochemistries. Interestingly, Proxima B's tidally locked nature could offer some protection. While one side of the planet faces constant radiation from Proxima Centauri, the dark side could act as a refuge. Subsurface habitats or deep caves could shield potential life forms from the worst of the radiation. Additionally, if Proxima B has subsurface oceans, these could provide a stable, radiation-free environment where microbial life could thrive, much like the ecosystems around hydrothermal vents on Earth. Despite these challenges, scientists remain hopeful that Proxima B's extreme environment offers a fascinating opportunity to study the resilience of life. By observing how organisms could survive or even thrive under such conditions, researchers can expand their understanding of what makes a planet habitable. Proxima B is not just a potential home for life. It is a laboratory in the search for life's resilience across the cosmos. The possibility of life on Proxima B raises more questions than it answers, but it also offers a new perspective on the definition of habitability. The search for life on Proxima B is not only a scientific mission but also a philosophical one. It challenges our understanding of what constitutes a habitable environment and broadens our search for life to include planets with extreme conditions. Proxima B's hostile radiation environment and tidal locking force researchers to rethink the traditional concept of habitability, which was previously based mostly on Earth-like conditions. One of the key aspects of studying Proxima B is its potential to reveal new insights into how life could adapt to harsh conditions. If life can indeed survive and evolve in such an extreme environment, it could redefine our expectations for where life might exist in the universe. Understanding these possibilities may help scientists focus on other exoplanets that share similar characteristics to Proxima B, expanding the criteria used to identify potentially habitable worlds. The exploration of Proxima B also fits into the broader context of the search for exoplanets, planets that exist outside our solar system. In the past few decades, the discovery of exoplanets has exploded, with thousands of these distant worlds now identified. The study of these planets, particularly those in their stars' habitable zones, has shifted our perspective on the likelihood of finding life elsewhere. Proxima B, with its proximity and potential for liquid water, is one of the most exciting candidates for the search for life. However, it is far from unique. As technology advances, the number of known potentially habitable exoplanets continues to grow. In addition to studying Proxima B, astronomers are focusing on planets around other stars, particularly those that share characteristics with our Sun. These Sun-like stars offer habitable zones that may be more stable and conducive to life. However, Proxima B's orbit around a red dwarf star offers a contrasting case that challenges traditional thinking about habitability. Its study can provide valuable lessons on the resilience of life and how it might exist in more extreme environments. Proxima Centauri, the star that hosts Proxima B, also offers researchers an intriguing opportunity to better understand stellar behavior, particularly the differences between stars like our Sun and red dwarfs. Red dwarfs are far more numerous in the universe than Sun-like stars, and studying these stars can help us understand how different types of stars influence the potential for life on surrounding planets. Proxima Centauri's frequent stellar flares and the effects of its intense radiation on Proxima B's atmosphere may help scientists learn how different kinds of stellar activity impact planetary environments, providing vital clues for the search for life elsewhere. For now, Proxima B remains a mystery. However, technological advances and future space missions may eventually provide the data needed to answer one of the most profound questions humanity faces. Is there life beyond Earth? With each new discovery, the possibility of finding life on Proxima B or other exoplanets becomes more plausible. The implications of such a finding would be profound. Proxima B's unique characteristics and its position within the habitable zone of Proxima Centauri make it one of the most studied exoplanets in recent years. While scientists remain hopeful about its potential to host life, the planet's extreme conditions raise important questions about what makes a planet truly habitable. One of the most intriguing aspects of Proxima B is its tidally locked nature, which means that one hemisphere is constantly bathed in sunlight while the other is in perpetual darkness. This creates an interesting dynamic in the planet's environment, with one side potentially facing scorching heat while the other remains freezing cold. The region in between these two extremes, known as the Terminator line, could offer a more temperate zone. This zone, where day meets night, might have conditions that are more suitable for life, with moderate temperatures and potential access to water in liquid form. However, the extreme conditions that exist between the two hemispheres of Proxima B also present a number of challenges for life to thrive. For instance, any potential organisms that may exist in the habitable zone would have to be resilient to temperature extremes and high radiation levels. Researchers are particularly interested in the potential for subsurface life on Proxima B. If the planet has oceans beneath its surface, these could provide a stable, protected environment where microbial life might survive, much like Earth's deep-sea ecosystems. These environments, which are not exposed to the harsh surface radiation, could harbor unique forms of life that thrive without sunlight, relying on chemical processes rather than photosynthesis. This presents a fascinating possibility for how life could adapt to alien environments far different from Earth. Moreover, Proxima Centauri's status as a red dwarf star raises additional considerations, for Proxima B red dwarfs are much more common in the universe than Sun-like stars, and they are known to have intense stellar flares. These flares are bursts of energy that release large amounts of radiation, including X-rays and ultraviolet radiation, which could severely impact any life on a nearby planet. The frequent flaring activity of Proxima Centauri could cause significant atmospheric erosion on Proxima B, stripping away any protective atmosphere it might have. This would make it much harder for the planet to retain an atmosphere capable of supporting life. Despite the challenges posed by Proxima B's environment, the planet remains a key target for astronomers studying the possibility of life beyond our solar system. The proximity of Proxima B, at just over 4 light-years away, allows for detailed studies using advanced telescopes like the James Webb Space Telescope, JWST. JWST's ability to detect infrared radiation gives it a unique advantage in studying the planet's atmosphere and surface conditions, providing vital data about its potential habitability. The study of Proxima B is not just about finding life, but also about expanding our understanding of what makes a planet suitable for habitation. As technology continues to improve and more exoplanets are discovered, scientists are refining the criteria used to identify planets with the best potential to support life. Proxima B offers a glimpse into how life might adapt to the extreme environments of other planets, and its study could help inform future missions to explore even more distant exoplanets with similar characteristics.